Let's take a look at how the level data is stored in Eggerland Mystery. Eggerland is a game for the MSX computer, released in 1985 and created by HAL Laboratories. You play as the hero Lolo, and you have to rescue the princess Lala. There are several enemies you'll encounter, such as Snakey, who simply blocks you, Medusa, who will instantly kill you if she spots you, Alma, who moves around a bit erratically and will chase you under certain conditions, Gol, who is stationary but will shoot fireballs at you if he sees you, and finally Skull, who will chase you down. The goal of every round is to open the exit door, which you do by collecting all the diamond framers in the round. This is what the first round looks like. Simply collect the diamond framers by pushing some blocks around and shooting some snakies out of the way, and then you make your way for the exit. There's 100 of these rounds, 5 special rounds for which you need a special password, and 10 bonus rounds. What we're after is to find out how these rounds are stored in the ROM of the game. As for the tools, I will be using OpenMSX, which has a built-in debugger. We'll mostly use the disassembly window, the memory viewer, the CPU registers, and we need to be able to add breakpoints and memory watch points as well. A good place to start looking for something related to the level data would be the current round number. Every time we load a level, the game has to look up which round number to load, so let's figure out where the round number is stored in RAM. For this, we'll use a tool called the Cheat Finder, which is obviously available in the Tools menu. And if we wait a little bit in the main menu, the demo will play. And the demo will play specifically in round 86, so we can search for this value in memory. So we look for 86 here, and we'll see we have 77 remaining locations, meaning there are 77 positions in RAM where the value 86 is stored. Of course, this doesn't give us an exact location of the address of the round number in RAM, so we have to do another search within these 77 values to pinpoint it further down. So let's just start the game now, and then we'll end up in round 1, so we can search for the value 1. We'll enter a dummy password and end up in round 1. So now we'll do another search within these values for the value 1, and we'll end up with 2 values, 2 addresses. So let's take a look at the first one here, C81B. We'll open the memory view and we'll go to C81B, which of course contains the value 1, which will now change to, for example, 9, and see what happens. I'll change it to 9, and we can immediately see that in-game the round number has updated. This is a very good sign, of course, that we're on the right path. But as an extra test, we will play this round and see if we skip to level 10, to round 10, when we exit this round. So let's play this round. We exit the level and end up in round 10. So this means that our assumption that the round number is stored in value or address C81B is correct. Now that we have the address where the current round number is stored, we can look in the disassembly where that address is being accessed. For that, we will make use of the watch point functionality. However, we have to position ourselves within the game right at the point where we expect the round number to be read, in order to load the rounds itself. The best place to do that would be just when we enter the password on the password screen. Let's see where we end up if we activate the watch point here and then confirm the password. So I will enter a dummy password. I'm not confirming it yet because we're going to add the watch point now of type read memory at address OXC81B. And we notice that the game has paused because this value is being accessed here. However, I haven't confirmed the password yet, so this probably has nothing to do with loading the level data. So let's continue. Now I will confirm the password. Right, now we are in round 1. At least we have painted the chrome, but we haven't loaded anything of the first round yet. So let's look what happens in the assembly here. We did indeed load C81B into the A register. Then we're calling a function at A824, and we notice that immediately after C81C, a different value is being loaded into the accumulator. That means that these two are probably related. So let's take a look what happens in A824. It starts right over here. Let's take an in-depth look. The first thing we do in this function at OXA824 is load a different value into the A register. It seems that loading the current round number into the A register, which we did before we called this function, was useless, as we're immediately overriding it with another value, but no big deal. The game loads the byte at OXC81C into the A register, which in our current state holds the value 0. Let's call this the mystery number, as we don't know yet what exactly this value does. It is highly suspicious though, as it is literally the next byte in memory after the current round number. Next, we load the value OX6056 into the HL register. This register is often used for 16-bit pointers, so let's treat it this way. Then, we AND the A register with itself. This seems useless at first sight. Why would we AND a value with itself? It would always return exactly what you started with. There is, however, a side effect. If the result of the AND operation is 0, then the 0 flag is set. Let's say we have a value of 5 into the A register, and we perform the AND. The result of this operation is of course 5. 5 is not equal to 0, so the 0 flag is not set. If our A register, however, contained the value 0, then we would AND 0 with 0, which has 0 as a result. So the 0 flag would be set. What we are testing for here is whether the mystery number is 0 or not. This is immediately obvious in the next instruction. We perform a jump based on the contents of the 0 flag. If the 0 flag is set, in other words, if our mystery number itself was 0, then we take a jump to address A833, basically skipping the next 3 lines of instructions. If the mystery number is not 0, then we do execute these 3 lines, which load a different pointer into the HL register, decrement the A register by 1, and take another jump at the end to A837. In our case, we do make the jump to A833. We load our current round number into the A register, which is round 1, so that's what gets put into the A register. Then we decrement the value in the A register and put the result back into the A register, and it will now contain the value 0 again. Let's take a step back and convert this into pseudocode. We start by noting down our 2 pointers to 6056 and 6080. Let's put these in 2 variables called data at 6056 and data at 6080. We don't know yet what these contain, but they do look important. We create a value called round number for the A register, which we initialized with the mystery number, and a so-called interesting data variable, which is basically the HL register and points to address 6056. The AND instruction combined with a jump form an if clause. We check whether the round number variable currently containing our mystery number is equal to 0. If it is equal to 0, we take the jump, so we override the round number with the current round number and decrement it by 1. If the mystery value was not 0, we don't take the jump, so we choose a different pointer for our interesting data and again decrement the round number by 1. Of course, the decrement instruction could have easily been outside of the if clause, but that's just how the assembly was written back in the day. Basically, we're pointing at a different set of data based on this mystery number being 0 or not. The decrement of the round number value containing either the mystery number or the current round number can also be explained. The current round number is 1-based. We are in round 1. However, if we need to index into an array with, for example, level data, we can assume that we'll want to index this with a 0-based value. In our current state, the mystery value is in fact 0, so the associated pointer is OX6056. Let's take a look in memory what we can find at that location. This is the memory that our interesting data pointer was pointing at. There were 2 pointers, 6056 and 6080. Notice that these 2 are not far apart. Unfortunately, this implies that these do not contain our level data yet. There wouldn't be enough room to fit all the information for 115 rounds. We'll have to look at some more of the code to figure out what is going on. Here's the section where we ended up after handling the if clause. Register A contains our current round number -1, which is 0, and the HL register contains our interesting data pointer pointing to 6D56. First thing we do now is compare the contents of the A register to the hard-coded value 5. For the first round, the A register contains 0, so if we compare 0 to 5, the side effect of that comparison would be that the carry flag would be set, because 5 is bigger than 0. The next jump instruction checks the carry flag, and if it is set, we jump out of the little area we are investigating to address A841. This doesn't give us much information, seeing as we are skipping the stuff we are interested in, so let's assume we are currently looking at round 15. So the A register would contain the value 14, or in hex OE. The carry flag would now not be set by the compare instruction and the jump would not be taken. Next, we subtract the hard-coded value of 5 from the contents of the A register, so that now becomes 9, and we increment the HL register twice. Then we jump back to our original comparison instruction and repeat the process until the A register is smaller than or equal to 5. The equivalent pseudocode would be this. We have our interesting data pointer pointing to the data at address 6D56 and our current round number -1. Then we execute some code while the current round number -1 is greater than 5. We subtract 5 from the current round number and increase the interesting data pointer twice. Why would we increment the HL register twice though? Remember, the HL register is used for 16-bit pointers. If we take a short peek ahead, we see that the value of what HL is pointing to is loaded into the A register. This proves that we do indeed treat the contents of the HL register as a pointer, so we need to advance 2 positions to skip this entire pointer value. The conclusion we can draw here is that the interesting data pointer doesn't point to the level data itself, but to another pointer. This makes that this entire region of memory is a list of pointers, seemingly separated by 5 rounds each. This actually makes sense, and the game gives us 2 hints that this might be the case. The construction mode in the game allows us to edit the first 5 levels, and after every 5 rounds in the game you get to play a bonus stage. Therefore, it makes perfect sense to separate level data per 5 rounds. Let's interpret this big list as a list of pointers like this. Note that F8D5 has been transformed into OXD5F8. This is because of endianness. We have to swap the values around if we want to interpret them as full 16-bit values. The list seems to contain 25 pointers, as I stopped when I encountered these zeros here. Those zeros would create an invalid pointer anyway. We already determined the rounds were split per 5 rounds, so this makes perfect sense. There are 100 regular rounds, so 20 pointers for those, 5 special rounds, so 1 pointer for these, and 20 bonus stages needing 4 pointers. This totals 25 pointers. There are a couple of interesting things going on with this list of pointers though. Let's take a look at the 4 last pointers. They seem to be 2 sets of the same 2 pointers. Remember our mystery number? That number determined whether the interesting data was pointing to either the beginning of this pointer list at 6D56 or in case it was non-zero at 6D80. This just happens to point at the last 4 pointers in the list. 4 pointers make up 20 rounds, as there are 5 rounds per pointer, so the conclusion is pretty clear. These last 4 pointers are pointing to the bonus stages, because the last 10 bonus stages are repeats of the first 10, and our mystery number is none other than the current bonus round number. Our complete function to locate the correct pointer to the level data now looks like this. The interesting data is now known to be the array of normal and bonus level data pointers. We check whether we are currently in a bonus round or not, and adjust the offset into the pointer array if we are. Then the pointer array is traversed until we arrive at the correct pointer based on the round number. Another curious thing about this list is the address of the first pointer compared to the 24 others. The 24 last ones all seem to be in the range of OX6E to OX8A, yet the first pointer is at OXD5F8. Let's take a look at how the memory is laid out when the game is running. We can determine that when the MSX loads the game, the ROM data is mapped at address OX4000. Without knowing how memory mapping works in the MSX, we can simply open up the Eggerland ROM in a hex editor and search for F8, D5, 59, 6E, etc. Basically the list of our 25 pointers. This list is found at address OX2D56 in the ROM, yet in the game the address is 6D56, a difference of 4000 hex. The ROM has a file size of 32 kilobytes or 8000 hex, so that means that it is mapped from 4000 to C000. The first pointer in our list of 25, D5F8, is therefore pointing outside of the ROM data, somewhere in the RAM section. To realize why this is the case, you do need to know how the game works a bit. There's a built-in level editor in the game, the so-called construction mode. You can design 5 levels on your own, save them to disk and exchange them with friends. However, when you leave the construction mode, the 5 levels you designed will replace the actual first 5 levels of the game. This is done so you can actually play your custom designed levels. The construction mode can obviously not override the data in ROM, so the first 5 levels need to be loaded in RAM, which can be perfectly overwritten and then loaded and played by the game. If we look at our memory again, we see the list of pointers at address 6D56. I've marked the pointer list in red. Now we look at the second pointer in the list. Its value is 6E59, again accounting for endianness, so we are swapping the 2 bytes. Address 6E59 is right here, so this chunk of data contains the information for rounds 6 through 10. Let's mark that in blue. You can already see where this is headed, but to be sure, let's see what data our first pointer in the list points to at address D5F8. The data at D5F8 starts here. When we compare the values at D5F8 with the chunk between the list of pointers and the data for round 6 through 10, we can clearly see that these values are identical. This means that even though there's no pointer in the list to this section, it clearly contains the level data for rounds 1 to 5, stored in ROM. This data is then copied to RAM when the game starts up, so it can potentially be overwritten by the construction mode. Now that we have access to the level data, we can start interpreting how this data is encoded. Round 1 looks like this. The data for the first 5 rounds, pointed to by our first pointer in the list, OXD5F8, looks like this. Without looking at the disassembly yet, we notice something suspicious. These triplets of zeros seem to repeat. Could these perhaps indicate the start of each of the 5 rounds contained in this block of data? The data for the 5 rounds would look like this then. Luckily, the game gives us a huge hand by providing a construction mode where we can not only create our own levels, but it also loads the 5 first level in the editor. That means we can actually alter the first round and see what changes we end up with in the exported file. First though, let's just save the first 5 rounds from the construction mode as is and inspect the saved file. This is the data in RAM for the first 5 rounds, and this is the exported puzzle created by the construction mode. The first 7 bytes of the file seem to be some sort of file header because the entire rest of the file is exactly the same as what we can find in RAM and ROM for the first rounds. Now let's go back to our construction mode, clear out the first round and add some power-ups. For the first round to be valid, Lolo and the exit have to be present. I've also added 3 diamond framers. The reason for this is that you can assign a number to each power-up. This number indicates how many diamond framers you have to pick up before the power-up becomes available. That information has to be stored in the level data as well, so you might as well experiment with that. I've chosen 1 diamond framer for the first power-up, 2 for the second and 3 for the third. The old save data looks like this, with what we assume to be the first round data highlighted in green, and the file header highlighted in orange. Then we have the new exported data of the mostly cleared out level. The header of the file seems to be nearly identical. Then we have some differing bytes, but the rest of the file is completely identical to our old file. A couple conclusions we can draw from this. The 5 rounds seem to indeed be separated by the 3 zeros we suspected before. Round 2, which was left intact, does seem to start with 3 zeros, 82, 88, AF, etc. The first 3 zeros of the new round 1 seem to have been replaced by 81, C2, 43. What stands out here is that these 3 bytes end with 1, 2, and 3. These are curiously the same number of diamond frames we chose for each of our power-ups. It does make sense that the 3 first bytes are power-up data, as for the first 5 rounds in the game, no power-ups are available. Hence, these values being 0. So that's where the triplets of zeros come from. The data for round 1 now also seems to be way shorter. This makes sense too, because the level is mostly empty. We see a bunch of OFs, followed by some other numbers, and then a couple more OFs. We've come as far as we can with the construction mode. Now we'll have to look at the disassembly to figure out how this data is structured. Finding the algorithm that decodes this level data shouldn't be that hard. We just have to put a read memory watch point on the first byte of the level data of round 1, right here at OXD5F8, and then start round 1 in the game. The level data should only be touched by the decoding function at that point in time. So let's add our watch point of type read memory at address OXD5F8. And again we break, but we haven't entered the password yet, so we can just continue execution. We enter the password, and now we do break at this LDIR instruction. We don't see any immediate reference to address D5F8 in the disassembly, but that makes sense. This routine has to be able to decode all the rounds, not just the first. Let's take a look at what this instruction does. The LDIR instruction copies data from the memory location pointed to in the HL register to the memory location pointed to in the DE register. It does so 1 byte at a time, but n amount of times determined by the contents of the BC register. Every time it is executed, it copies 1 byte, increments registers HL and DE, and decrements register BC until it reaches 0. Looking at the code, the BC register is loaded with a hard-coded value of 3 here, so the LDIR instruction will copy 3 bytes. This strengthens our suspicion that the first 3 bytes are related to the power-ups, as there are 3 possible power-ups in each round. The DE register is loaded with the target pointer OXD87B. This is an unknown memory location, but it does make sense that you would copy the data out of the stored level data and into some other location you can manipulate. For example, when the power-up has been used up. If you need to reference this data later on, you don't want to have to look up what the current round is, find it in the 25 pointers, find the correct level data within the block of 5 rounds, and look at those 3 bytes then. You'll want to put this data in a fixed known location for easy access, which is exactly what the programmers of the game did. The HL register is not explicitly set in this piece of code. It has been set before this function was called, and it does indeed contain D5F8 when we inspect it. Basically, we are copying the first 3 bytes out of our level data to some unknown memory location. This is then immediately followed by a copy of the next 2 bytes to memory location OXD88A. At this point in time, we have no idea what these 2 bytes represent. Next, we load address OXC000 into the DE register. Address C000 is interesting because if you remember the memory layout, you will recall that the ROM was mapped at address 4000 hex and its size was 8000 hex. Add the 2 together and you end up at address C000. We'll have to keep an eye on that memory location. It will most likely be involved in decoding the level data. Now we take a look at what code that unconditional jump to address A506 leads us to. At address A506, the target of the previous jump, we find this entire function. It looks quite daunting, but we will take it step by step. The HL register now has address D5FD in it, pointing to the 6th byte of the level data. Remember, we copied 3 bytes presumably for the power-ups and 2 unknown bytes, so now we are pointing at the 6th byte, which we load in the A register. For round 1, this contains the value OXA5. Then, we AND this with the hard-coded value of 7F. It's easier to look at this in binary. Basically, we ignore the top bit and extract the bottom 7 bits. The result of the AND operation, which is OX25, is then written into the A register. Immediately after, in the next instruction, we copy this value into the B register for safekeeping. We want to keep this value around, and lots of instructions manipulate the A register, so we have to save it temporarily in the B register. We continue by reloading what HL points to, the 6th byte of our level data, into the A register. We apparently want to make another manipulation of the 6th byte, so we have to fetch it again, as the previous instructions overrode the A register. Let's ignore this increment instruction of the HL register for now. It's not super relevant to our understanding of the level decoding algorithm. It just progresses the HL pointer to the next byte, the 7th of our level data. It only indicates that more than likely we are done processing the 6th byte of the level data. We again do an AND operation on the 6th byte, this time with the value OX80. Let's again look at this in binary. This AND operation checks the top bit in the provided value. The reason why the exact outcome of this operation isn't that relevant is because of the next jump instruction. This jump is conditional on the 0 flag. If the 0 flag is set, then the jump will be taken. If not, we just carry on. That means that the top bit in the 6th byte of the level data determines whether we jump or not. Let's take a look at what we jump to, address OXA55C, which is beyond the current routine we are looking at. Notice that both this new segment and the remainder of our original code end with a return instruction. The jump, conditional on the outcome of the top bit being set in the 6th byte, chooses which section of code gets executed. That makes it a simple if clause. If the top bit is set on the 6th byte of the level data, we do not take the jump and execute lines A511 to A547. Otherwise, we execute A55C to A572. It looks like we have two algorithms to decode the level data chosen by that top bit. Let's see what we've learned from this disassembly so far. The first 3 bytes are most likely power-up related and copied elsewhere in memory. We don't have any idea yet what the 4th and the 5th byte do, but they're also copied somewhere else in memory. The 6th byte is split into 2. The top bit determines which algorithm, and the bottom 7 bits are still unknown. Before we dig into the assembly to figure out what these bottom 7 bits represent, let's inspect our level data for round 1 again. The total amount of bytes for round 1 is 43. The header, 3 bytes for power-ups, 2 unknowns, and 1 byte we are currently thinking about, consists of a total of 6 bytes. 43 minus 6 happens to be 37, which is the exact same value we decoded by taking the bottom 7 bits of our 6th byte. Clearly, it's the amount of bytes we need to process to decode the level. This also makes sense, as we already knew that the level data for all rounds had variable lengths. There is some sort of compression algorithm in play, and you need to know how many bytes to process to decode an entire level. Also, seeing as the rounds are grouped per 5 for each of our 25 pointers, you need to be able to traverse this block of 5 to get to, for example, the 4th level. You just need to read the 6th byte of each round, take the bottom 7 bits and skip that amount of bytes to reach the next round. This is the first potential level decoding algorithm we encountered, and this is chosen if the top bit of our 6th byte is actually set, which happens to be the case for round 1 of the game. At this point in time, register HL contains a pointer to the 7th byte of our level data, and register DE contains a pointer to OXC000, presumably a working area where we will put the decoded level data into. When you're confronted with a slightly longer function such as this one, it's always interesting to first take a global look and look for things that stand out. There are a couple of instructions that are necessary because of the limitations of the machine, such as all the stack pushing and popping and register exchanges, but they don't really affect our interpretation of what's going on. The first thing I notice is this. We are loading the hard-coded value of OXOB into the A register and then saving it somewhere in memory. OXOB is of course 11 decimal. This stands out because an Eggerland round consists of an 11 by 11 board. To decode level data, surely we need to track our current X and Y positions, so loading 11 in memory is a good sign. The next thing that stands out is this. Register HL containing our 7th byte of our level data, or rather the first byte of the actual level, is being ANDed with OX07 and OXF8. We've already seen a similar manipulation with the 6th byte, where we included the algorithm choice in the top bit and the data length in the bottom 7 bits. let's take a look at these values in binary to see how the split of this next byte is done. Clearly, we are separating the bottom 3 bits from the top 5 bits. If we now look at our code and look at what we actually do with these extracted values, we see this. The bottom 3 bits are stored locally in the C register, which is then incremented by 1. The top 5 bits get copied over to OXC000, the pointer that resides in register DE. The next section does some shuffling around with pointers, but we do see the value 00OB popping up again, another representation of the decimal value 11. At the beginning and end of this section, we are pushing and popping onto the stack. Our C register did contain the bottom 3 bits, and we don't want to lose this information, yet we do need to work with the C register for some reason. By pushing and popping, we ensure we can mess with these registers without losing track of our original bottom 3 bits. The add instruction does the bulk of the work here. It adds the value of the BC register, which we loaded with the value 11, to the pointer that is in HL. Before we do that though, we exchange registers DE and HL and swap them back after we do our addition. Again, this convoluted process is just a result of the limitations of the machine. The add HLBC instruction exists. The add DEBC instruction, which would have been perfect for this situation, simply does not. So we have to swap some data around. We are adding 11, not to our 7th byte, which resided in HL, but to the OXC000 pointer. Next, we again do something that is level coordinate related. At the start of the function, we had loaded the hard-coded value 11 into memory location OXD912. Now, we simply load that value back into the A register, subtract 1 from it, check whether it's 0, and jump somewhere outside of this function if it is, and save the decremented value back to memory address D912. In short, we are keeping track of two 11-related counters. The first one kept at address D912, which is decremented and checked for 0, and the second one by jumping 11 places forward in our decoding destination memory starting at C000. Makes perfect sense when we are dealing with an 11 by 11 board. Next up is this section. The C register, which contains the bottom 3 bits of the level data byte we are currently handling, is subtracted by 1 and checked for 0. If we check the jump target address, it looks like we end up at the place where we write the byte to our C000 area. Of course, not to C000 exactly, as that pointer is increased by 11 each time we run through this little loop. If we do hit 0, HL is incremented, meaning we go from the 7th byte to the 8th byte in our compressed level data, and so on. The conclusion we can draw here is that the bottom 3 bits represent the amount of times the top 5 bits need to be written out to our target decoding area of memory. All the rest is coordinate positioning and memory and register management. If you have some experience with programming, you might recognize this way of storing data. It's a simple run-length encoding. As Wikipedia says, run-length encoding is where consecutive occurrences of the same data value are stored as a single occurrence of that data value and a count of its consecutive occurrences. Let's see how the memory area at OXC000 gets filled up when we run this algorithm one write at a time. On the right, you can see round 1 with a grid overlay, and on the left, the memory area at C000 being filled up by the algorithm 1 byte at a time. It seems this algorithm fills the board vertically first, then horizontally. That explains why we add 11 to the OXC000 pointer every iteration to reach the next position in the same column. It looks like Lolo in the top left corner has identifier OX88, whereas walkable space is 08 and walls are the value 0. Let's see if our analysis is correct by decoding a couple bytes manually. The level data for round 1 looks like this, with the actual run-length encoding compressed data highlighted. As a reminder, the bottom 3 bits plus 1 is the repetition amount, and the value to repeat is represented by the top 5 bits. Byte 1 has a value of OX88. The repetition count is the bottom 3 bits plus 1, which is 1. The value to insert is represented by the top 5 bits. So we insert Lolo with ID 88 at the first position, obviously once. Byte 2 has a value of OXOF, so the repetition count is 8, and the value to repeat is also 8. Note that the maximum repetition amount we can encode this way is 8. We have 3 bits for the amount available, which gives us a range of 0 to 7, and 1 is added to this to change the range to 1 to 8. It doesn't make sense to have 0 as a repeat count, obviously. The stretch of walkable space in the first column that spills over into the second column has a repeat count of 11. Because of the 3-bit limitation, we do have to split this up into 2 instructions, the first for a repetition of 8 and then one for 3. Remember how the top bit of the 6th byte of our level data determined whether we would execute the big algorithm or the small algorithm. Let's now take a look at the smaller algorithm in detail. We immediately notice the ANDing with OX07 and OXF8 again, after reading in the current byte of our compressed level data. This is exactly the same as the previous algorithm, so it looks like the encoding of the repeat count and value is identical. In other words, the same run length encoding algorithm is in play. Notice, however, what happens when we write the value to the DE register, which contains OXC000. We simply increase the DE pointer. Instead of adding 11 to skip to the next position in the column, we skip to the next one horizontally. The conclusion we can draw is that the first big algorithm is a vertical encoding algorithm, and the second one is a horizontal one. To make sure, let's look at how OXC000 gets filled in when we load a level that uses the second algorithm. An example of such a level would be round 5, as shown on the right. The memory is indeed being filled up horizontally, so this confirms that this second algorithm handles the decoding in a horizontal fashion. In modern-day computing, memory space is not really an issue. Back in the early 80s though, you had to seriously consider every option to cram as many bytes in your ROM cartridge as possible. In this case, they only had 32 kilobytes to work with. When we take a look at the size of all the data of all the levels in the ROM, conveniently stored sequentially, we see it ranges from OX6D88 to OX8B97. That's a total size of 7,695 bytes, about a quarter of the entire cartridge ROM. If you simply look at certain levels, you can immediately tell whether they are better suited for a vertical or a horizontal algorithm. Round 1 and 5 are perfect examples of that. We can't just guess the developer's intentions though, so let's verify this. I've written some C++ code that can retrieve all the rounds from the ROM and decode them. I've also implemented both horizontal and vertical encoding algorithms, so we can re-encode all the levels with both algorithms and see if they went for the smallest option each time. Here's a list of the first 20 rounds in the game, the length of the horizontal and vertical algorithms, which algorithm produces the smallest result, and the algorithm that was chosen by the developers. The chosen algorithm in the ROM is consistently the smallest size possible. This definitely proves that calculating both algorithm sizes and picking the smallest one is exactly what they did in the early 80s when the puzzles were being created. Some statistics. If only the horizontal algorithm was used, the total byte count would have been 9,070 bytes. If only the vertical algorithm was used, the total byte count would have been 9,333 bytes. If the optimal algorithm was used, the total byte count is or would have been 8,273 bytes, and if the worst algorithm was used, the total byte count would have been 10,130 bytes. Note that the discrepancy between 8,273 bytes for the optimal algorithm and the previously mentioned 7,695 bytes, as is actually present in the ROM, is due to the fact that the last 10 bonus levels are duplicated, but they are present only once in the ROM. It is just in our list of 25 pointers that the last 2 are identical to the previous 2. In these statistics, I counted the extra set of bonus stages as well. If I only count rounds 1 to 115, I end up exactly with 7,695 bytes. Now that we have figured out how to decode the run length encoded data, we'll go back to the first 5 bytes. The first 3 were related to the power-ups, and the next 2 were still unknown. The 6th byte, of course, contains the algorithm choice and the compressed data length. Both sets of data, the first 3 and the subsequent 2 bytes, were copied to a different memory location by way of the LDIR instruction. If we put a read memory watch point on the first target memory location at OXD87B, we end up at this piece of code. For some reason, we are using the LDIR instruction again to copy the same 3 bytes to yet another memory location at OXD235, so we'll put a read memory watch point on that location instead. This watch point triggers during every frame of the game loop and checks whether the correct amount of diamond framers has been picked up and the power-up needs to be activated or not. At the top of this code, we are loading the 3 different power-up values residing in D235 through D237 into the HL register, and for each of these 3, we call the function at OX5700 just underneath. For power-up 3, the code just falls through, of course, no call instruction necessary. Immediately, we see 2 AND operations being performed, first with OXC0 and then with OX3F. In binary, those look like this. Again, we are storing multiple pieces of information inside the power-up byte, this time in the top 2 bits and the bottom 6 bits. We obviously know which types of information we need to store. It's the identifier of the power-up, be it nothing, arrow, diamond framer, or bridge, and the amount of diamond framers we need to pick up to activate the power-up. Logically, we can assume that the top 2 bits give us the identifier and the bottom 6 the amount of diamond framers. 2 bits gives us a possible 4 distinct values, and the bottom 6 gives us 64 possibilities. If we go in construction mode and we experiment with the diamond framer counter for the power-up, we see that it tops out at 63 for this exact reason. Note that it is technically possible to have more than 63 diamond framers in a round, but because of the 6-bit limitation, the maximum we can reference is 63. I guess back in the 80s the decision was made that 63 as a maximum was a decent compromise. Now all that remains are the 2 mystery bytes in our level data at position 4 and 5. When we put a watch point on the 4th byte, we end up here. We notice the values being loaded, both the 4th and the 5th byte, are immediately followed by a call to OX6705. Now, this code isn't very clear. We're calling functions, setting memory locations, and we don't have a clue what they do. In my reverse engineering before tackling decoding the level data, I had already labeled several memory locations, and then they popped up here, giving me an immediate clue as to what was happening here. This is the same code, but with some extra labels for these memory locations I had previously figured out. This gives away the secret immediately. The 4th and 5th byte in our level data stores the position of Lolo and the exit. The call to 6705 does a conversion, which I go deeper into in the blog post that accompanies this video. It ended up somewhat of a dead end though. Instead, we'll take a more closer look at the values we encounter for the 4th and 5th bytes and what the corresponding rounds look like. Let's start with round 1 again. Lolo's position, stored in byte 4, is 0. The exit position is in byte 5 and has the value OX85. It could make sense that Lolo, being in the top left corner, would have a coordinate of 0, but the OX85 for the exit doesn't make immediate sense. If we overlay the 11 by 11 grid, however, this time a 0-based grid, things start to become more clear. The exit is located at column 8 and row 5. The stored value in the level data is OX85. The x-coordinate is simply in the top nibble and the y-coordinate in the bottom nibble. Lolo would then of course be in position 00, and if we look at other rounds, it is easily confirmed that this is indeed how the 4th and 5th byte work. At this point, we have completely figured out how the level data of an Eggerland Mystery round is encoded. There is something peculiar going on with the file header of puzzle files. If we save the first 5 rounds with the construction mode untouched, the file looks like this, with the file header highlighted. This file header is not part of the level data, but if we look closer, we see some numbers we recognize. Let's rearrange the bytes a bit. If we account for NDNS, there seem to be 2 pointers in there, 0xD5F8 and 0xD6C9. The first pointer, D5F8, is of course the first pointer in our big list of 25. It represents the start of the first 5 rounds. These rounds take up 209 bytes, and if we add this to 0xD5F8, we get the second pointer in our file header, 0xD6C9. It looks like these pointers specify the range of data we need to overwrite in RAM when we load our custom rounds. Specifying start and end pointers of this new data leads me to believe that they might have intended to replace other sets of 5 rounds, not just the first set of 5. These pointers would indicate where to write this data. Of course, the decision was made to only load the first 5 into RAM, which is overwritable, so it's not really possible to overwrite, for example, rounds 6 through 10. Let's look at the code where reading the file header is being handled. After the first byte on disk is loaded into register A, which is done with a call to OXA6B6, there's a comparison with the hard-coded value OXFE. This looks to be a magic number to identify Eggerland Mystery puzzle files. Then we see 4 bytes being read and basically thrown away. Our 2 pointers reside in bytes 2, 3, 4 and 5, yet here they are completely unused. Another hint that they intended to make it possible to load custom levels above the first 5 rounds, but ultimately scrapped the idea and just ignore these bytes. Bytes 6 and 7, which always seem to be zeros in the file, look like they are special. The 2 combined bytes are written to location OXFCBF, and then the 2 bytes are ORed together. If the result of that OR is not 0, a small jump is taken, skipping the line, storing the hard-coded value of D5F8 into the DE register. This load instruction loads the target address of the first round into the DE register, where subsequently all the bytes of the puzzle file will be copied into. Basically, these 2 bytes, if non-zero, prevent the right target pointer being set to our well-known value. Another hint that the writing of round data was dynamic enough to target other pointers. When we look at the file writing routine though, the 6th and 7th byte always seem to be written as zeros. The file loading code, when reading from tape, is slightly different when it comes to what is skipped when the OR of byte 6 and 7 results in a non-zero flag, but it ultimately leads to the same result. I wonder what the reason was to decide to only allow the first 5 rounds to be overwritten. Was it lack of available memory, or was it the complexity of managing overwriting variable-sized chunks of data? If the puzzle file contains a chunk of data that is bigger than the original 5 rounds in memory, you'd have to shuffle some memory around to allow them to fit. Unfortunately, the answer to this question cannot be easily deduced from the code we have in front of us. Now that encoding and decoding of level data has been figured out, the in-game construction mode can be recreated online in JavaScript. This is exactly what I have done, and the link is available in the description. You can create your own levels, import either the original rounds in the game or a puzzle file from a friend, and export so you can load them in your favorite emulator or machine. Of course, I have dumped all the original rounds from the ROM. The link to this page is also available in the description. This information has of course been available since the 1980s, as people were figuring out the solutions to the puzzles and sharing that information with friends. Now, however, we can more easily see the more secret stuff, such as the exact water flow directions, respawn locations, and bullet framers. Lastly, I've made an online repository for all custom-made Eggerland levels. It's a database that stores the individual rounds, but also 5-packs and ROM packs. A 5-pack is simply a collection of 5 rounds, just like you would export from the construction mode. A ROM pack, however, replaces the original 115 rounds with all new rounds. You simply have to provide the Eggerland ROM file, and the website will overwrite the data in the provided file with the new rounds. Creators of ROM packs also have the option to change the 20 secret passwords for the rounds, as well as a special word. All information about Eggerland Mystery reverse engineering can be found on zapatic.net. That concludes our delve into the level storage algorithm of Eggerland Mystery. If you want to watch me reverse engineer games like Eggerland live, you can follow me on my Twitch channel, or if you have any remarks or questions, feel free to post them in the comments below. Happy reverse engineering!